Wonderful. Well, thanks very much for having me. I wish I could be there in person, obviously. I think Paris is always a wonderful place to visit. Um, what I thought I would do in my time, and I'll try to leave plenty of time for questions. I know this is a topic that all of us are thinking about a lot. I wanted to step back and think about what are the implications of AI for economic growth, and bring together some things I've thought about in several different papers recently, including the paper I wrote with Philippe several years ago. And I'm currently, working more on this topic, and so I'll highlight a little bit of the stuff that I'm doing. In fact, I think Chris Tonetti is at the LSE right now presenting for the first time our joint work, but it's too preliminary for something like this. We just got a first draft of the slides yesterday, so but I'll allude to some of that work now. So in the paper with Philippe and Ben Jones, we highlighted two key themes. One was that it might be productive to think about AI as the latest form of an automation process that's been going on for hundreds of years. So Joseph Zeira was the first one who kind of made this point about automation being since the Industrial Revolution. And we thought that was a productive way to view AI, in that you could look at the history of automation and hope to learn something about the future of AI. And so in the past, we had, steam engines and electric power and computers, and in the future, we kind of already have driverless cars and pathologists, but maybe we automate researchers and maybe everyone. So that was the first point. We can use the history of automation to help leverage some insights into AI. And the second insight was that AI may be limited by Baumol's cost disease. And so one way to think about this is with an elasticity of substitution less than one, so that tasks are complements. In that case, economic growth and productivity are constrained not by what we do well, not by the stuff that the computers are really good at, but instead by the tasks that are essential, tied to labor, and hard to improve. And that perspective turns out to be, I think, quite useful in seeing how AI may affect the economy. It might not be the right perspective. I think that's an open question, but it's certainly a useful perspective to consider. So obviously there are a ton of work in the area of AI and growth. Certainly Daron and Pasquale's work, kind of every year it seems like they write another great paper on this topic. David Amos and Morten Olsen, Ben Jones and Liu, I'll refer to their paper in a little bit as well. So that's just some examples of the work. Okay, so automation and this Baumol effect, how do we think about it? So here's the basic economic environment that Philippe and Ben and I started to work with. And you see there's nothing especially especially surprising about the framework. Tasks with an elasticity of substitution less than one, so tasks are more complementary than Cobb-Douglas. That's going to give rise to this Baumol force. The tasks between 0 and beta have been automated, so you can produce them with capital. The tasks between beta and 1 have not yet been automated, so they can only be produced with labor. In fact, you could also do the ones from 0 to beta with labor, but there's a simple condition that we assume holds, so that you don't want to do that. And then beta is changing over time. I'll talk about how it changes over time in a second. That's left out of this slide. And then the rest of the model is just totally neoclassical, standard. You got a bunch of capital and a bunch of labor that you need to allocate to these different tasks, and fixed investment rate, just to keep things simple. Okay, if you recognize the symmetry of this problem, well, you realize you're going to take your total stock of K and spread it over the tasks from 0 to beta. So each task gets K over beta units of capital, and they're beta of those tasks. And so, the reduced form of the previous slide, the production function looks like this, where the beta, oops, sorry, that one doesn't work as well. The beta and the 1 minus beta enter twice, right? There's the green beta and the purple beta to look at the capital. And you can see capital per task is K divided by beta. And then the number of tasks that's the purple beta. The number of tasks that have been automated, that's the green beta, right? And so there's this sort of race between these two forces. On the one hand, as you automate more tasks, that kind of, is an increase in the importance of capital. On the other hand, as you spread a fixed amount of capital across more tasks, capital per task goes down. Which of those two effects dominates? Well, with sigma less than 1, the purple effect dominates. And so the dilution effect dominates, and we're going to see that on the next slide. You'll notice exactly the same thing applies to labor. Labor's getting squished on a smaller and smaller set of tasks. So 1 minus beta is declining as beta rises. And that means L divided by 1 minus beta is going up. Labor per task goes up because the number of tasks labor is doing goes down. So labor's getting concentrated, capital's getting diluted. If you collect the beta terms, you can express this task-based model in reduced form as a standard CES production function where there's a B times K and an A times L. And if you look at what the B is and what the A is, B is 1 over beta to the 1 over 1 minus sigma power. Hi, come on in. Sorry, my students are grabbing some exams. And because sigma is less than 1, I've written it so that all the exponents are positive here. An increase in beta, you can see, reduces B, right? And that's the capital dilution effect dominating, right? Similarly, an increase in beta, because the exponent's positive, raises A. And this was kind of, I think, one of the key surprising things that Philippe and Ben and I kind of discovered, which is that automation in reduced form is neither a change in B or a change in A only. Instead, it's a twist, right? It's a decrease in B and an increase in A. And in some ways, that's kind of surprising. You might have thought, oh, automation should be like an increase in B. No, it's a decrease in B with the elasticity of substitution less than 1. The dilution effects dominate. And it also is an increase in A. So even though you're automating more tasks, that looks like labor augmenting technological change. And we kind of know that's good news from the standpoint of Yuzawa's theorem that, you kind of want labor augmenting technological change if you want to get some kind of balanced growth path, if you want to match the data, say, for the last 150 years. Okay, so an increase in beta, an increase in automation, lowers B and increases A. So now, how does the automation occur? We also model that in kind of a very much a reduced form way, but I think it's a natural way. Suppose that a constant fraction of the tasks that we've not yet automated get automated every period. So look at the stuff we haven't automated. Suppose 5% of that stuff gets automated every year. That's this law of motion for beta, and theta would be the 5% in that case. 1 minus beta is the share of tasks you haven't automated. Theta is 5%, so that explains how beta changes. Notice in this setup, beta converges to 1, right? Eventually, 99.999, you never get to the 100%. It's only an asymptotic result, but, beta is converging to 1. So what happens to 1 minus beta, the share of tasks done with labor? Well, that obviously converges to 0. But the interesting thing is with this law of motion, the growth rate of 1 minus beta is constant. 1 minus beta falls to 0 at a constant exponential rate, which is also given by theta. So the growth rate of 1 minus beta is negative theta. The fraction of labor tasks falls at a constant exponential rate. And again, constant exponential rates are very helpful from the standpoint of balanced growth. So putting all this together, we've got this reduced form CES production function, f of bk comma al, where b and a are given by the terms before. Beta is going to 1, right? And so b is asymptoting to 1. B is eventually going to be constant. B is asymptotically constant. What about a? Well, remember, 1 minus beta declines at a constant exponential rate. So 1 over 1 minus beta rises at a constant exponential rate. And that means that a grows at a constant exponential rate, right? The growth rate of a is given by theta, this rate of automating tasks that have not yet been automated, divided by divided by 1 minus sigma, right? And so an interesting thing here is that if a constant fraction of the remaining tasks get automated every period and sigma is less than 1, then the model features this asymptotic balanced growth path that satisfies the Uzawa theorem. B is going to be constant, A is going to be growing at a constant exponential rate. And so you just get a standard neoclassical balanced growth path. In fact, you can also show another thing we often care about in these models is what happens to the capital share and the labor share. Well, asymptotically, the capital and labor shares are going to be constant. And you might have thought, hey, if we're automating tasks, if beta is going to 100%, surely the capital share goes to 1 or 0 or something. No. In fact, the capital share levels off at some number that could easily be 1/3, and the labor share levels off at some number that could easily be 2/3. You can see the capital share is given by this beta term, which is going to 1, multiplied by the capital output ratio to the sigma minus 1 over sigma. And so that converges to S over G plus delta raised to a negative power. And if S is greater than G plus delta, which it kind of needs to be here, you get a capital share less than 1. So the interesting thing here, the second interesting thing, maybe I talk about this on the next slide. Yeah, let me go here. Okay, so we talked about beta going to 1. Labor per task rises exponentially over time. There's a constant population in this simple example, but it gets concentrated on an exponentially shrinking set of goods. So effective labor grows exponentially. Labor gets 2/3 of GDP, let's say, for the right parameter values, even though labor tasks are vanishing. And that's exactly this Baumol effect, right? Labor gets squished onto the things that only it can do. And because the elasticity of substitution is less than 1, the scarce factor gets the share, right? And so labor gets squished onto a vanishing set of tasks, but those tasks are essential. All the capital tasks, yeah, those are easy. Computers are great at those, but the price effect, kind of means they don't get 100%. And so labor ends up with 2/3 of GDP, even though it's working on a vanishing fraction of tasks. So it was interesting that the automation model kind of has this flavor. Okay, notice a couple of limitations. So first, it's only an asymptotic result. It only occurs as beta goes to 1. So it's not clear this is relevant for the US or France or other modern economies today. This is where the follow-up paper by Ben Jones and Liu comes in, and I'll talk about that in a second. Yeah, but that was a limitation to what we did with Philippe. So yeah, this brings us to the paper by Jones and Liu. And the key insight they had is that in fact the balanced growth path can occur today with beta less than 1 rather than asymptotically if you add capital augmenting technological change. So you add faster computers. So instead of the yi equaling ki for the stuff that's been automated, let yi equal zi times ki. There's some capital augmenting technological change on each task. And let's call that z. Well, in their setup, which kind of makes some normalizations, the capital share ends up being the ratio of beta to z. So on the one hand, as you automate more things, the capital share goes up. As beta goes up, the capital share goes up. On the other hand, as z rises, as computers get more productive, as computers get cheaper, the capital share goes down. And so there's a race between beta and z. And you can see if it just so happens that beta and z are rising at the same rate, then the capital share can be constant even with incomplete automation. And this was a really nice, elegant insight, and I think it's quite useful and pushes our modeling and understanding of these topics forward in a useful way. One thing that they did that I don't totally love is they kind of remember beta is going to 1. So in order to get the capital share remaining stable, you need the z automation to eventually stop in some way. And so they rig things in a just so fashion so that it gets harder for computers to get better on more advanced tasks so that beta over z ends up being constant. It seems to me that doesn't have to be the case. Instead, another natural result is if beta goes to 1, maybe z continues to rise. Our computers continue getting better, even as automation gets, levels off. And that implies from this simple equation here, as z rises and beta stops rising, the capital share falls to 0. And that's an even stronger version of the Baumol effect going on here. With sigma less than 1, the ever declining price of computers, the fact that computers are getting more productive, Moore's law, they're getting cheaper when you quality adjust. Well, the scarce factor gets the share. Computers are becoming, incredibly unscarce as they get better and better because of Moore's law. And so you'd expect in this framework, perhaps as beta levels off, the capital share to fall to 0. Even though labor is getting squished on a vanishing fraction of tasks, it gets the share, right? And again, this is very much driven by the sigma less than 1, but it's a really interesting prediction of this type of model. And this brings me, this last point is one that Chris and I have been thinking about in our new work. We want to take the model I've shown you so far and generalize it in various ways, and then apply it to this question of how much of growth is due to automation historically, right? Do some quantitative exercise. So how much of growth in agriculture, in motor vehicles, in software, in the aggregate economy, other key sectors, how much of growth is due to automation? What's the quantitative answer to that question? And then we'll kind of use that to speculate about what improvements in AI might do over the next decade, kind of using history as a guide. Well, one of the things we found, one of the facts I like a lot that's very much related to this, this last point here, is ask yourself, what is the share of factor payments, not just to capital, but what does the share of factor payments to computers look like over time? What share of GDP is paid to computers? And it turns out it's very easy to look that number up in the BEA total factor productivity accounting. And this is what you find. You find, before 2000, in the 1990s, during the dot-com boom, the factor share paid to computers was rising. But since 2000, the factor share of GDP paid to computers has fallen from 3% to just over 2%. It's been declining for the last 25 years. And this is exactly what the model kind of predicts. It says, look, as computers get better and better because of Moore's law, you might expect in the long run the price effect to dominate, and the fact that computers are getting cheaper in a quality adjusted sense drives their share down. And that's exactly what we see in the data. And what's interesting about that is when you try to extrapolate what's the effect of AI going to be on the economy, I think this fact that computers are accounting for a smaller and smaller fraction of GDP is actually quite informative. It kind of supports that sigma less than 1 view of the world. Okay, let me press on. The next thing Ben and Philippe and I did was look at AI and automating the idea production function instead of the goods production function. And very much we kind of use the same insights we've gotten so far. Let me ignore automation on the goods side. So make the goods production function just be produced with labor and with ideas. Here now A is going to be the stock of ideas. And let the idea production function be the thing where the automation occurs. It's now got the CES and these tasks, these X's, and the X's initially are done with labor, and over time you learn how to do them with capital, exactly as we've done in the setup so far. Let beta be the fraction of tasks that are automated at date t, and not surprisingly, you get this same CES reduced form in BK, and now I'm calling it C times S. S is the labor scientists. S is the labor used to produce ideas. And I'm using C because I'm using A already for the stock of ideas. I have too many letters here. But B is 1 over beta to the power. C is 1 over 1 minus beta to the power, just like before. Okay, well, if you think about what happens with sigma less than 1 and constant returns in the F, you can factor out the CS. And in the long run, this CES term is just C times S times some constant. Okay, And so with continuous automation, the idea production function ends up looking very much like the kind that I write down in all of my papers, right? That it's kind of the number of researchers times a to the phi, capturing the knowledge spillovers. The only difference is there's this extra term c, right? And remember, c is the 1 over 1 minus beta to some power. So that's where the automation effect shows up. And so c is growing at a constant rate, s is growing at a constant rate, the population growth rate. And so the growth rate of a settles down to gc plus gs divided by 1 minus phi, right? And with gc equals 0, that's the standard thing that I often see in my papers. But now there's this extra term. You get this boost from continued automation from GC. Notice, for example, if GS were 0, if there were no population growth in scientists, you'd still have growth in this example because the number of scientists is getting squished onto a smaller and smaller number of tasks. So scientists per task grows exponentially, even though the number of scientists is not. And that could sustain growth. Right? And so GC here is going to be 1 over 1 minus sigma times the fraction of tasks that get automated, theta. And you could get this boost to growth. Now, an interesting question is, can AI raise the growth rate? And what you see here is, well, if automation's been going on for the last 50 years, and all of us, a lot of our research tasks are getting automated, that's been going on for a long time. That just delivers constant growth. If you want growth rates to increase due to AI, one way to do it is to have theta increase, right? So suppose the fraction of tasks that get automated actually increases. AI is just faster at automating stuff than what we were doing before, then growth could accelerate. So that's one way to get growth rising. And an extreme version, the other thing to do is now change the automation process. Rather than saying, a constant fraction get automated every year, suppose everything gets automated. Suppose all research tasks can be done with capital. Well, then you get a different result, which is the idea production function uses machines and ideas to produce new ideas. And if phi is greater than 0 in this example, you could see the exponents add to more than 1, and you could get a growth explosion. So it's certainly possible to get this exploding growth in this framework, either because the fraction of tasks that get automated by AI rises, or because AI can do everything, and then machines produce ideas, gives you more machines, gives you more ideas, and that positive feedback can give you explosive growth. So one thing I've been thinking about recently is, what would AI accelerating economic growth look like? What would the next 10 years look like if this is really going on? And how would you tell the story? And I find this exercise to be helpful. And let me just walk through it. So I think what you'd see in the near term, which we're already seeing, is productivity boosts from AI. So think about software. So software is the place where AI is having arguably its biggest impacts right now, which is it's incredibly helpful at coding, right? So Cursor AI, I use it every day basically to help me in my research, and it's great. You can now with Claude Codex, OpenAI Codex, you can one-shot large numbers of tasks, and Claude Opus 4, the claim is that it can code for several hours straight. Well, we're already seeing productivity boosts from that, and I think 25% here is conservative. That's the number I put in last year, and probably I should raise that number. So a question to think about: is it possible that over the next decade, let's say, is it possible that AI agents can automate most coding? That seems like it's very much baked in. And I think Dario Amodei and Sam Altman say, that's happening, now, maybe by next year. So next decade is giving it a lot of time. So AI automating coding seems baked in the next several years. And then you ask the AI, hey, code up even better AI agents. Help us create better AI algorithms, help us create better AI agents that can use the computer and use the browser, and that gives us even better AI agents. So there's some feedback effect there that seems like it helps in automating software. Well, Moore's law continues, so prices decline, AI agents get cheaper. Eventually, we get millions of virtual research assistants helping us with cognitive tasks, right? And one way to envision that is think about, I have a Zoom call with my RA, and I ask my RA, hey, help me with this project, do this task, do this coding, check this math, maybe derive this result that I don't have time to derive, right? Anything you can ask your RA to do over Zoom, well, your RA could be a virtual agent instead of a human being, and the AI can go away and do those tasks. Maybe not perfectly today, but in the next 10 years, is it plausible that with all of this automation, with all of this feedback into AI creating better AI, is it possible that cognitive tasks, anything that could be done by a remote Zoom worker, could be done by a remote virtual research assistant? That's not beyond comprehension. That seems like it could happen. And some of the cognitive tasks, of course, are inventing ideas, come up with better AI algorithms, come up with better economic growth models, come up with new drugs, come up with new materials, come up with better medical technologies, come up with designs for better computer chips, right? All of those are the kinds of things that millions of virtual research assistants working in the cloud, taking advantage of Moore's law, let them work 24/7. And yeah, it seems like those things get better. That would raise productivity as well. Then the next step, I think, is you ask them to design better robots, simulate the real world, come up with new designs for robots, new designs for hands, new designs for grippers, new designs for, transportation technologies, etc. And then we build the robots. And then when you've got AI and robots and AI running the robots, everything is potentially automatable at that point, I think. And so that's kind of, I think, that, one view of what accelerating growth would look like. And it seems completely plausible to me that that could raise productivity enormously over the next 2 decades, and therefore raise growth rates substantially for the next 2 decades. 2 decades. That's a possibility. Okay, I don't want to claim it's locked in. I don't think it's locked in, but it's not clear where in this argument, where do we fall off the train? Where do we say, oh no, that step, maybe before that is okay, but after that, I don't see that happening. It's not so clear, why each step couldn't follow from the previous one. Okay, so that's the optimistic case for growth and automation. Let me give you the pessimistic case. So in every talk I give, I have to show this graph. It's special to me, right? Growth in the US over the last 150 years, straight line on a log scale, 2% growth. The reason I like this graph is it sort of gives the counter argument to the story I just told, which is, economic history suggests that things might not be as easy as the story I just laid out. So electricity and computers absolutely changed the economy, but it took 50 years to do so. And so I think one of the clear lessons of economic history is things take longer than we expect. That seems totally plausible for AI as well. The other point, though, sort of again from this graph, if you think about it, this was, Joseph Sears' point at substance. Automation's been going on for 150 years, and yet growth rates have not sped up. So over the course of this chart, we had electricity, the internal combustion engine, the transistor, the semiconductor, the internet, smartphones, DNA, gene sequencing, and yet growth was 2% per year despite all of that, right? And so how do we understand? How do we put those facts together? Well, maybe those great ideas are simply what kept growth from slowing. Maybe the way to view growth is that you have these regimes of general purpose technologies and you get lots of applications of them for a while. But if you don't get the next general purpose technology, growth inherently slows down. Ideas get harder to find within a technology. And so you need the next big idea to keep growth going. And in some sense, over the last 150 years, there's always been a next big idea. And that's simply what allowed us to maintain 2% growth rather than having growth slow. And so in this telling, perhaps AI is the latest great idea that lets us maintain 2% growth for a while longer. Okay? That to me is the pessimistic view. I've given you the optimistic view and the pessimistic view. I probably lean more to the optimistic view, which may be surprising to you because, I've emphasized this graph for so long. But I do think it's important to lay out the pessimistic view as well. Okay, let me skip the labor market point. I know I'm running out of time. I wanted to say just a few words about catastrophic risk, because I think this is a topic that economists have not talked a lot about, but I think it's actually potentially very, very important. So I think there are two versions of this existential risk that in my reading and talking with people seem as a way to summarize it. There's the bad actor version and the alien intelligence version. So the bad actor version, I think, is very plausible. And that is, suppose we think about Claude 6 or GPT-6 or whatever. Could a bad actor use, a state-of-the-art model 5 years from now to cause serious harm to large numbers of people? Absolutely. You ask this oracle that's incredible at automating lots of cognitive work, you ask it, help me design a COVID virus that's 10 times more lethal and takes 3 weeks for people to display symptoms, and then you build that and release it. Is that something a bad actor could do with ChatGPT-6? Maybe. In some sense, nuclear weapons were manageable because they were so rare. If every person had them, which is kind of what the bad actor GPT-6 view is, then maybe it wouldn't have ended so nicely, at least so far. Okay, the second version of existential risk is the alien intelligence version, and this feels much more science fiction-y, but I think it is worth considering. So two lines about this. Suppose this afternoon we got news from scientists that they've observed a spaceship out near Jupiter on its way to Earth. How would we feel about that? Some aliens are coming to the Earth. I think we'd be excited, but maybe 10% we'd worry maybe this doesn't end well. After all, in the history of the Earth, when advanced civilizations encountered civilizations that were behind, it didn't end well for the party that was behind. And then I was on a panel with Stuart Russell, who's a CS professor at Berkeley, who's like the co-author of the key textbook they use in first year CS on artificial intelligence. And he had a quote that I liked a lot. He said, how do we have power over entities more powerful than us forever? And that's a question worth thinking about. And if you think about it, it doesn't seem so easy to solve. Okay, so let me just talk, very briefly about the two papers that I've written on this topic, and each one I only have one slide for. So I'll try to finish in the next 4 minutes so we have some time for questions. So in the first paper, I sort of asked what I think of as the Oppenheimer question. Suppose if nothing goes wrong, AI is amazing. It accelerates growth to 10% per year. Let's give it let's do the most spectacular thing we can imagine, maybe. But there's a one-time small chance that it goes horribly wrong and AI kills everyone. So do you use it or not? Do you press the button or not? What risk are you willing to take? Are you willing to take a 1% chance of killing everyone to get 10% growth forever, or lower than that, or higher than that? Okay, and you can write down the framework and you learn some surprising things. So for example, if you have, one of the findings is that with high living standards and lots of risk aversion, so if gamma is 2 or 3, you only take tiny risks, maybe 2% or 0.5% if gamma is 3. And that's kind of what I expected to find. With log utility, it turns out you're willing to take a 1 in 3 chance of killing everyone to get that 10% growth. So I used to think I was log. Now I don't think I'm a log utility person at all. The second finding was probably more surprising to me, although with the benefit of hindsight, I should have known it. If AI is good enough to accelerate growth to 10% per year, it's probably also going to cure cancer and heart disease and help us live longer. Well, it turns out in that scenario where AI can cut mortality rates in half, even with risk aversion of 3 or 4, you're willing to take huge risks, like 25% risks. Why is that? Well, now you're comparing lives and lives, not lives versus consumption. Lives versus consumption, the diminishing returns, diminishing marginal utility, means you don't want to do a lot of that. But lives versus lives, I don't care what kills me, whether it's AI or cancer. I just don't want to die. And if AI can cut the risk of cancer, I'm willing to take some risk of the AI doing bad things. Okay, and then the last paper that I've just been working on recently is how much should we spend to reduce AI's catastrophic risk? So suppose we take what I've said so far seriously. How much should we be investing to make AI safer? And I didn't work on this for a while because I thought, yeah, maybe it's hard to think about. If there are lots of future generations, you'd invest a lot. And I kind of knew that point. But I had an insight over the winter break, which is we've already faced this risk. The COVID pandemic was an example of this risk. In the COVID pandemic, we all faced a mortality risk that turned out to be 0.3%. And in exchange, we shut down our economies, right? We spent something like 4% of GDP to mitigate a mortality risk of only 0.3%. I would suggest the AI risk is probably at least that large. And so in some sense, we ought to be willing to spend something like 4% of GDP by revealed preference. And that suggested to me we were massively underinvesting. If you take the value of life seriously, it turns out you get even bigger numbers. And so I won't go through that in detail now. I wanted to stop to leave us some time for questions. But I suspect we're wildly underinvesting in mitigation spending because lives are so valuable. And it does depend on how effective is the mitigation spending. And that, you kind of have to look at the paper, but I do a bunch of simulations. And it really supports this notion that, should we invest 0.5% of GDP in AI safety? Almost surely, yes, I think. Okay, so final thoughts. I'll give you just 2 questions. How much will AI change things between 2015 and 2045? More or less than the internet changed the world? I think probably more. The fact that it takes 30 years instead of 5 years, I think is probably good to know, but not the critical point. The fact that it's going to change the world in profound ways, I think is the important point. And then, yeah, I think we're probably massively underinvesting in mitigating risk. I will say one policy that I think is worth considering: should we tax GPUs, tax NVIDIA chips, and use the revenue to subsidize safety? It seems to me that's the Pigouvian tax that one would want here. Okay, let me stop there. Thank you very much.